Determine the primary dimensions of the gas constant over the universal gas constant. So I'll just stop. That's just a warm-up activity, okay? And you just do that. All right, so what is R and what is R sub U? R sub U is maybe 8.314 kilojoules per kilomole Kelvin. Where'd that come from? Your memory, right? You've used it so many times, you know that one. Or if you had to go refresh your memory, it's an equation sheet or cover of the textbook, true? But what is R? Is it equal to RU over the molar mass? If you then clue that in, then skip RU, because the ratio of R over RU is equal to RU over the molar mass. RU, they cancel. So the units on R over RU is equal to the units of 1 over the molar mass. Oh, now I have to remember the units on the molar mass. Was it kilograms per kilomole? And is a kilomole one of the 7? Yeah, it's an amount. So it's amount over mass. So amount over mass. And in SI units, it's kilomoles over kilogram. How many got that? Good? Very good. Let's go on. Boundary layer growing along a thin flat plate has a boundary layer thickness of delta. So this is a problem where you have a sharp edge plate, flow comes at it, and you pick up a region that senses the presence of the flat plate. And inside that region, it's fluid, but the fluid is slower than the free stream out here, where it's all just V, because it's felt the presence of a stationary flat plate. So this is what they call, this region in here is the boundary layer. And the thickness of the boundary layer, delta, is a function of the distance from the leading edge, x, and the free stream velocity, v, and the fluid density, rho, and the fluid viscosity, mu. So now determine a dimensionless relationship for the thickness of the boundary layer in terms of x, the distance from the leading edge, v, the velocity of the free stream, rho and mu, the properties of the fluid. So we'll make a list: delta, x, v, rho, mu. Do we have any other parameters? No. Count them up. How many do we have? 5. So what is that? K is equal to 5? Or is it n? I forgot. N? N is equal to 5. Now bust it into its basic SI units, or dimensions. I like to work in SI units. So what is this one? Meters. What is this one? Meters. What is this one? Meters per second. What is this one? Kilogram or mass per meter cubed. And the last one, kilogram per meter second. You've done it a couple of times, right? So how many primary dimensions do we have? 3. So how many pi groups should we look for? 2. So it's 5 minus 3 is 2. So we'll build, because we want to, first of all, you want to get a dimensionless relationship for the boundary layer thickness. So that'll be a building block of one of the pi groups. And then look at your other ones and pick the one that's kind of complicated. And I like to pick viscosity. You can see viscosity as kilogram over meter second. Density is just kilogram over meter cubed, only 2. And V is just 2 of them, meters over second, and X is meters. So pick the more complicated one, which is mu. So the first pi group that we build, we're using the Buckingham pi method or theorem or algorithm. Okay, so we'll say delta, and it has units of meters. So I'm going to separate that right there. And so what do I do to get rid of it? Any suggestions? I can use x, v, or rho to make it dimensionless. I can multiply by x or divide by x. I can multiply by v or v squared or divide by rho or multiply by the square root of rho, whatever I want to do to make that term dimensionless. The term is right now has dimensions in m for meter. You're sleeping on me. Just divide by x. If you divide by x, put a meter there, it's canceled. There's your first pi group. Not that hard, right? The next pi.
You don't always have to use all the variables?
No,
Okay.
do not have to use them all. Now, if after you make all your pi groups, some of the variables are missing, go back and redo it. Okay?
So I guess we have to use some of these and not these.
Yeah, otherwise, there won't, let's say I did it, but V never showed up in any of the groups. Well, then V's not going to be able to, and you said, you started with the assumption that V was going to be important. If you changed V, but you'll miss it. So now the second pi group, I like to start whenever I have viscosity 1 over mu. Why? I don't know, but I'm anticipating a Reynolds number. The Reynolds number, rho v d over mu. So if I'm going to start with a more complicated parameter, viscosity, I can put it in the numerator or denominator of my pi group, put it in the denominator. I may not get a Reynolds number, maybe I do get a Reynolds number. Can you see why I'm starting that way? Because mu is in the denominator of the Reynolds number. Otherwise, I'll develop the inverse Reynolds number as a dimensionless pi group. Okay, so I look at my units for that one, and it's meters second over kilogram. So now I want to do something. I look and I see kilogram is only in rho. So I'm going to use rho to get rid of the kilogram in mu. So if I multiply by rho, then I'll have kilogram over meter cubed, and the kilograms go. True? Now I just have meters and seconds. I need to use V next to get rid of seconds. Use V to get rid of seconds. So if I multiply by V, meter per second, succeeded in getting rid of seconds. Now I can use X to clean up the X. So I put an X here. Whoops, let me change color. X. And then that'll be meters. And I think now we have meter cubed in the numerator and meter cubed in the denominator, and it's dimensionless. Okay. And did we get something that looks like a Reynolds number? Sure. Rho v x over mu. And so the bottom line for this is we would expect that the boundary layer would grow delta over x equal to a function of the Reynolds number, where the Reynolds number characteristic length is the distance from the leading edge. It's just x, the distance from the leading edge. Okay. See, a lot of times they have the Reynolds number based on diameter, Reynolds number based on length. Here it's Reynolds number based on x. X.
So what do you do with the first pi group?
Oh, that was on the left-hand side of my equal sign, because it's implied I want to determine a relationship for the boundary layer thickness in terms of. Yeah, so I put the pi group that had the boundary layer thickness in on the left-hand side. Any other comments? Yes?
How is this useful once you try and make that comparison between like a model and a prototype?
Well, what you might do is have a smaller test section, and then you're modeling the thickness boundary layer growth, okay? And then you can extrapolate to a larger test section or larger experiment. In this case, it's a little bit abstract because it's very simple. You're just growing the boundary layer. But let's solve another problem and see how we have to get similarity. What I'd have to do is, in one case, if I came in and I said, well, the Reynolds number at that location is, let's say, 10 to the 5, okay, or something, 10 to the 4 or something. I would come up here and I would get the measurement of the thickness of that boundary layer in that case. Then I could go to the other one, match the Reynolds number, which tells me the distance from the leading edge, basically, and it depends on the velocity. See how the Reynolds number is the velocity, it's the distance from the leading edge. Here, it's the velocity, distance from the leading edge. I could change fluids. From one case, I could have air, maybe I have water, I could have oil, but I have to match that Reynolds number for similarity, and then I can predict the similar behavior, the scaling. A periodic Karman vortex sheet is formed when a uniform stream flows over a circular cylinder. So the cylinder is here, the flow is coming here, and you get the shedding of vortices, and that's called, after the person that studied it, a Karman vortex sheet. All right. Determine a dimensionless relationship for the vortex shedding frequency. So I want to know f of k, the frequency. Frequency, just stop for a minute. Shedding, vortex shedding frequency. What units would that have? 1 over time, right? Right? Isn't it 1 over time? So it's how many are being shed per second, right? So we can think about just putting the units right there of inverse seconds, right? Isn't that frequency? Agree? A function of the free stream speed, v, meters per second, fluid density, rho. Rho is kilogram per meter cubed, and fluid viscosity, mu, kilogram per meter second, and the cylinder diameter, d, in meters. So how many variables or parameters do I have? 5. And then how many fundamental primary dimensions? 3. How many pi groups should I look for? 2. I want to build one around that frequency. What's the next one I want to build around? Yeah, let's build it around viscosity because it's the more complicated one. And once you've done a few of these, you fall into that pattern, right? And so I'll start the first pi group. Maybe I'll put it over here. Pi 1 is equal to in the numerator, that frequency. And so below it, I'm kind of keeping tabs. I have 1 over second. Well, there's nothing with time by itself, is there? But I have to deal with that second to get rid of it. What do you think? Yeah, divide by v. That'll go meters per second. And then multiplied by d, meters. And now it's dimensionless. True? So there's our first dimensionless group. Let me erase this. What about the second one? Well, I like to start with 1 over mu. And so it's it's meter second per kilogram as the unit. Get rid of the kilogram by multiplying by rho. Kilogram per meter cubed. So get rid of the second by multiplying by v. Get rid of the last length by multiplying by d, and it is the Reynolds number. So what we find, the result would be that the vortex shedding frequency times diameter divided by the fluid velocity we expect to just simply be a function of the Reynolds number based on the diameter. And the Reynolds number based on the diameter is the rho of the fluid, velocity of the fluid, diameter of that cylinder divided by the viscosity of the fluid.
And again, you chose the fluid viscosity just because.
Well, it's the more complicated. It has 1, 2, 3. So I want to build a pi group around the more complicated one. Yeah. What you might do is, if you got a bunch of data, you would collapse the data into this one pi group, f of k d over v. The second pi group would be the Reynolds number. Maybe the data plotted like that, and you would fit a curve to it, and then use that curve fit in future cases. Right? Okay. I just made up the trend in that. I don't know which way this one goes, if it's, down and up or down something. Here's another one. The speed of sound, c, in an ideal gas is a function of the ratio of specific heats, K, absolute temperature, T, and the specific gas constant, R gas. Determine a dimensionless relationship between these parameters. And so I'm going to stop and see how far you get. But you have to be able to remember what are the let me start, I guess let me do that. What are the dimensions of C? C is what? The speed of sound. So meters per second. Ratio of specific heats. CP over CV. So what are the dimensions of that? Unity, dimensionless. Just dimensionless. How about temperature? Temperature, Kelvin. And then the gas constant, R. What is it? Do you remember? It's kilojoules per kilogram Kelvin. Is that true? And then it's also meters squared per second squared Kelvin. Kilojoule per kilogram. Well, 1,000 meters squared per second squared is 1 kilojoule per kilogram. So you can work in either one of these. They're equivalent, but you can see which one's going to be more interesting or more helpful, right? Do you recall that 1,000 meters squared per second squared is 1 kilojoule per kilogram? That's why I wrote it either way for that gas constant. All right, I'm going to pause and see how far you get. All right, so we determined that there's 1, 2, 3, 4 parameters, but there's 3 primary dimensions, hence there's 1 pi group. And you can build it around almost any of them, they all are going to contribute. But what did you find? That let's start with R gas, which has meters squared second squared Kelvin. Looks like I'm going to use C to get rid of seconds. So divide by C squared, meters squared per second squared. Not only does it get rid of seconds, it gets rid of meters. And then Kelvin, I'll multiply by temperature, Kelvin. And this dimensionless K can go anywhere. Put a K right there. And that's equal to a constant. That's how you would express this result. The pi group is equal to a constant. And if you recall from previous work, the speed of sound for an ideal gas is the square root of K, R of the gas, absolute temperature. Now, this dimensionless result didn't give us the answer all the way. You know, this is just saying we recall this from previous study, but the Buckingham pi and dimensional analysis just says that, you know, that this group is equal to constant, and also that k could have been down here, that k could have been squared. Because k is dimensionless, it doesn't force it to be anywhere, right? But we'll put it right there. Okay. And if in this case that constant is just 1, but there you go. All right, ready to move on? So a lot of times you can look for established dimensionless parameters. So the drag coefficient, we've seen that one. It's given a symbol c sub d. What would it be? The drag force divided by some other force, usually dynamic pressure times an area. Dynamic pressure, 1/2 rho v squared, and then an area. So if the flow is coming toward an object like that, it's the projected area of the object. All right. Euler number. Well, what would that be? Some pressure loss or pressure drop. Let me look at my notes here. Some pressure drop or pressure loss divided by the dynamic pressure, 1/2 rho v squared. The Froude number, we don't use much, but if you're doing surface water, resistance, boats, or channels, or flow like that, where you have a free surface with water, you would use it a lot. So civil engineers, as well as naval engineers, but mechanical engineers still know of it, but we don't use it as much. It's a V divided by the square root of GL. So sometimes you can understand or interpret this. This is drag force divided by the dynamic force. Okay, this is a pressure loss divided by the velocity pressure, dynamic pressure. Here, it's not quite so easy to see, but it's a ratio of inertial to gravitational forces. Okay, what about the lift coefficient? I'll have to scoot over here. C sub L. It's a force of lift, like on an aircraft wing. And it's related to the dynamic pressure, 1/2 rho v squared, times some area to turn it into a force. And that area, though, is in the area of the direction of the lift. And so if your flow is coming this way and your structure is this way, the lift is that way, and so the area is looking down. You know, that's the projected area there. Okay, so sometimes it's what they call a plan form area. It's the view from the top. Mach number is the ratio of the speed of the fluid divided by, or the speed of the object in the fluid divided by the speed of sound in the fluid. And that Reynolds number, and there's a lot of Reynolds numbers. Just sometimes they put it rho Vx over mu, Reynolds number based on length, rho VL over mu, Reynolds number based on diameter, blah, blah, blah. It typically is, this is put as a subscript to indicate what is the dimension, what is that length. for the Reynolds number. And the Reynolds number can be interpreted as a ratio of inertial to viscous forces. Inertial to viscous forces. Having developed dimensionless relationships, similarity now allows the prediction of behavior for a new system based on previous observations. So they've studied copper before, they tabulated the thermal conductivity of copper and have put it in the table. You're an analyst, you're working somewhere for a company, you need to use the thermal conductivity of copper. You go to a table and you trust the result. Is the copper that you put into that machine tested? No, but you're trusting the measurements of copper made before. Well, here you're just expanding that concept. You're trusting measurements of pressure drop or drag force made before, tabulated in correlations, and now you apply them in your design. All right. So the terminology is out there, model and prototype. So when you want to predict the behavior, go back and forth, you have to have similarity in the systems. And so you have to have first geometric similarity. You need to scale it properly, right? Let me go ahead and pause right now. All right, here's the problem. It's a lot. You know, when you get these problems, they're long because it's all this information. You got to get information about the model and then the prototype. In this textbook and a lot of engineering textbook, prototype means the full scale. Model, smaller. So 1/4 scale model, so the model being 1/4 of the prototype of an airplane is to be tested in water. This seems very weird. You're going to test an airplane in water. The airplane has a velocity of 700 kilometers per hour in air at negative 50 degrees C. The water temperature in the test section is 10 degrees C. Why do they tell us these temperatures? Because fluid properties are a function of temperature, especially viscosity. And for the dynamic similarity, we want to match the Reynolds numbers. In order to achieve similarity between the model and the prototype, the test is done at a water velocity of so much. Here are the properties of air at that negative 50, 1 atm, and properties of water at 10. So the density and viscosity. If the average drag force on the model is measured to be this much, what does the drag force on the prototype? Use that data to predict the drag force on the prototype. Make sense? I pause and just see how far you can get. Okay? How would you approach this? Okay, the way it's worded, it already assumes that you've kind of done the first half of the chapter, which means that you've already seen the pattern, that drag force a function of some length scale of our model, some fluid velocity, some fluid properties. And so embedded in this is a drag force embedded in a dimensionless coefficient. The drag coefficient is a function of the Reynolds number. Okay, and now that's our launching spot. So what we do is we say, does our Reynolds number of the model match the Reynolds number of the prototype? If it does, then I don't have to know the detail of this functionality. I just know if the same Reynolds number is put into the same correlation, I'll get the same drag coefficient each time. So then the drag coefficient of the model is equal to the drag coefficient of the prototype. So how do we check the model versus the prototype Reynolds number? Well, we take a look at what do they say about this 1/4 scale model. That means the length scale in the model is equal to 1/4 the length scale of the prototype. True? Okay. So a couple ways you can do it. I can say, here's the Reynolds number of the model. If I divide it by the Reynolds number of the prototype, I want to find out what that ratio is. If it's 1, those two Reynolds numbers are the same. I have dynamic similarity. And when I have dynamic similarity, I can infer then the drag coefficient is going to be the same. Okay. So what is my definition of the Reynolds number? Rho of the model, V of the model, some length scale of the model, viscosity of the model. How about of the prototype? Rho of the prototype, velocity, prototype, length scale, prototype, viscosity, prototype. Okay. So we'll try to stick in some numbers. For the density of the model was conducted in water, 999.7 kilograms per meter cubed, and the prototype in air, 1.582, times the velocity in the model 393 kilometers per hour, the prototype 700 kilometers per hour. The length scale of the model divided by the prototype is 1/4. Use this information right here. 1/4. And the viscosity of the prototype, 1.474 times 10 to the minus 5 divided by 1.307 times 10 to the minus 3. And when you make that computation, it's 1.000275. It's not 1, and so we have to give up. Oh, come on, it's close enough to 1 for engineers, right? I would have probably accepted it if it was 1.1. Close enough. True? Just, it's close enough. But somehow they work these numbers so it's 1.000275. It's spot on. Textbook problem. Okay. Now that we've determined that the Reynolds numbers are the same, we can say that the drag coefficient is the same. So the drag coefficient of the model is equal to the drag coefficient of the prototype. What's our definition of the drag coefficient? It would be the force of drag on the model divided by 1/2 rho of the model, the velocity of the model squared, times the area of the model, equal to the same for the prototype. Force, drag, prototype, 1/2 rho, prototype, velocity, prototype squared, area prototype. Now, these the areas, we don't know exactly the area, but the areas are proportional to length squared. And so if I do the area of the prototype divided by the area of the model, it's the length of the prototype divided by the length of the model squared. It's geometrically scaled. Okay, so if one length is changed to be 1/4, then the other length changed to be 1/4, and then the area is changed by 1/16. Okay, I'm going to run out of room here, but let me kind of scroll down just a little bit, and you try and write it where you have the force, drag force on the prototype is the drag force on the model times the density prototype over density model, velocity prototype over velocity model squared, and then that ratio of areas, but the areas come into lengths. Length of the prototype over length of the model squared. And we had that the force on the model was 13,800 newtons. The density difference 1.582 divided by 999.7. The speed 700 divided by 393 squared, and it was 4. Length of the prototype is 4 times larger, so it'll be 16 times. And we calculate that the predicted drag force, if we went and built the full scale prototype, it would be 1110 newtons. All right, that makes sense? A lot of work, isn't it? A lot of steps in there. Reynolds number independence. So a lot of times you'll make some experiments, and the experiments will show the drag coefficient as a function of the Reynolds number, and it'll be, for low Reynolds number, it'll be highly dependent. But then for higher Reynolds number, it won't be highly dependent. It'll actually be flat. And this happens a lot. And so for high Reynolds number flows, the drag coefficient is Reynolds number independent. It doesn't depend on it. All right. Anybody look at, maybe you're aficionado of new cars, and you're looking at the aerodynamic drag on new cars, and you can go out and you can look at the drag coefficient for new cars and old cars, and they compare them, pickup trucks and all kinds of cars. It's that drag coefficient right here quoted as a single number for an automobile, because the automobile driving down the road is out in the turbulent regime, out in the Reynolds number independent regime, and it just quotes a single number. And that number could be something like 0.25. I think that's the number for my car. You could find all kinds of cars out there. You know, you can find a 1987, whatever, Lincoln Continental if you own that. You can find the Ford F-150 from 1980. And then you can find the 1995 Ranger. Something like that, okay? But that you'll see that they really compared 0.22 and 0.46, and that's a single number, and it's the aerodynamic drag on your vehicle as a single number. It's out in that region where it's Reynolds number independent. Okay. So as soon as you learn that the drag coefficient is a function of the Reynolds number, and then you see some people reporting the drag coefficient as a single number, you're tempted to say, unfair, they don't know what they're doing, they're wrong. But they're reporting a single number for high Reynolds number flows. Here's a problem. Water flows through a long straight pipe. The pressure loss is measured in a section of pipe having a length of 1.3 meters, and the diameter of that section is 10.4 centimeters. The average velocity and pressure loss is shown in the table. So they did some experiments. They had the velocity measured. You can visualize that as being the control. They slowly increased the velocity, took some measurements, moved to the next velocity, took some measurements of the pressure loss, and the pressure loss went up as the velocity went up. Predict the pressure loss at an average speed of 80 meters per second. Well, did they make any measurements at 80 meters per second? No, they stopped at 50. This is a case where you'd like to justify extrapolating the data, and if it's in a Reynolds number independent regime. So what we remember is that we have a pressure loss, and we cast that in dimensionless terms. What was that? We divided by the 1/2 rho v squared. Sometimes they give it a name, sometimes not. But here in this chapter, did they call that the Euler number? So the Euler number is a function of blah, 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 but it's a function of the Reynolds number. Okay? So what you do is you take the velocity, and if I know here, what is the definition of the Reynolds number? Rho, velocity, diameter over mu. Okay, for all of these test cases right here, V is changing, but is D diameter changing? Same diameter. Is rho changing? No. Is mu changing? So all you have to do is take this V, and you multiply that V by rho D over mu, and you get Reynolds number, and you put that in a new column in your Excel spreadsheet. Now you have dimensionless Reynolds number. You started with V, you got dimensionless Reynolds number. How about the Euler number? You take that PL. Well, I would do it in two steps. I would get what I call the velocity pressure, P velocity. And so the velocity pressure is just 1/2 rho V squared. I just use this data right here. Let me change color. Bring it over, and I get the velocity pressure column as a separate little entity. Intermediate step. Then I'll take the pressure loss and divide it by the velocity pressure, and I'll get the Euler number. And I'll take this data, the Euler number, on the y-axis, and I'll take this data, the Reynolds number, on the x-axis, and I'll look at it and how it plots. And this is how it plots. The Euler number as a function of the Reynolds number. For that exact data, it's very steep in this region and very flat in that region. So what do we say about this region? Reynolds number independent. So if I said it's at this Reynolds number or this Reynolds number, did the Euler number really change? No, it's the same Euler number. So can I extrapolate with confidence to a higher speed? Sure. And so a higher Reynolds number. So even though I didn't have any measurement for 80, I'm going to say that the Euler number is around 0.608 something. 0.6085. I don't really have 4 significant digits to it, but that's what I'm going to do, right? I'm going to put an average value there. And once I have that, then I can predict the pressure loss at that speed. So what I would do is I would come over here and I would get the velocity pressure at 80. True? And I'd say the Euler number was 0.6085, and I'd unravel the Euler number. So the Euler number is pressure loss, velocity pressure. So the pressure loss is the Euler number times that velocity pressure. That velocity pressure times that Euler number gives me a prediction of the loss, pressure loss. Look good? I'm going to stop for a minute.